Okay, since we have checked that everything is good with the data, we go to the next step, which will be the multi-QC. So multi-QC is not necessary because it's a summary actually of FastQC. But since quite often we will have several FastQ files to analyze, not just one that we have here, we have one perdent file here, then I think it's useful to demonstrate how to use multi-QC as well. So multi-QC does not do any analysis, that it takes the results from FastQC and makes some nice report. So multi-QC aggregate results from bioinformatics analysis into a single report. Okay, so FastQC on data 2, I guess this is what we need. Which tools has used to generate logs? Okay, this is not BAM tools, but it's FastQC. FastQC is the tool that we use to generate reports. So multi-QC can output reports for several tools. That's why here we have to specify which tool, for which tool we want to summarize and aggregate results. And since we want to show all the results from FastQ in a single report, we have to choose here FastQC. So insert FastQC output. I'm not sure if I should choose the web page or the raw data. We'll start with the web page. Probably I should use the raw data, but let's see what it will tell me. Yeah, maybe didn't like it so much. Okay, let's go for the raw data then. Yeah. So we have to use the raw data from FastQC to proceed with the report. And again, we have to wait here because the command and the data are uploaded to the server. And we have to wait. Okay, we see here that multi-QC report is ready. We saw already in FastQC that results are good. So I want to emphasize, to say here that if this is not actually what's happening all the time, we see quite often that that at the end of the reads the quality drops dramatically. So here it's the same that we saw previously with the FastQC, but we have both of the forward and the reverse made together. So we see that the quality is actually pretty good everywhere. But quite often you see low quality in the beginning or low quality at the end. And then if we see this case that we see low qualities at the edges, we have to use some trimming tool. So I just wrote here trimming, and the tools that we usually use is either Sickle, Trim-O-Matic. I have used both of them, and I have used also Trim Galore. So all of them, what they will do is that they will shorten a little bit the reads, removing some base pairs from the beginning and the end if they are of low quality calls. Here this is not the case, so we will not apply trimming here, but keep in mind that you may have to apply it for your data after you see the multi-QC control here. Again, it's the same report as we saw previously with FastQC, so I will not go through that, but the quality of the data is pretty good. Okay, and since we have good quality data, we can proceed with mapping. So I just wrote here mapping, but I'm not sure that this is the right keyword for that. Yeah, because it reports here several tools. That is not comfortable, but since I know what tool I want to use, I use BWA, and then I will go for this one, map with BWA, map short reads less than 100 base pairs. If you remember, our reads are 36 base pair long, so I have to go for this specifically aligner. Typically with human data, for example, or with data that we have nowadays, probably this is a bit older data, we use BWA mem or BWA mem2. So this is BWA mem and this is BWA mem2. But BWA mem is better for reads that are more than 100 base pair long. And this is not the case for our data, which are 36 base pairs. So I choose this one, and here is what I have to use. And the first question is, will you select a reference genome from your history or use a built-in index? Okay, so what is a reference genome here? I have the reads and I need to map them somewhere in some genome. And which is this genome? It's a reference genome. Galaxy has several built-in indexes or genomes already in the system. If the genome is not here, or if you want to use a special genome, I don't know what special genome will be, but there are some. There are, for example, some versions of the human genome together with viruses and so on. But yeah, if you want to use something typical, then probably you will find it here. And the yeast genome is something pretty easy. Just write here Cerevisiae. No, not here. Here I want to use a built-in index, and using a reference genome I go here and I type Cerevisiae. And this is the genome, the reference genome for the yeast that we're going to use. I already mentioned previously that the data is per dent. So we go for per dent data. And then the first pair is this one, but the second pair is not this one, it's this one. Good. We don't really need to set advanced options, and I just press execute. Now before I will press execute, let's see here what it writes. So what we run probably is this BWA ALN command. And here it provides some help that you can actually go through and read it while when you will run this for first time. Okay, so again the job is here and we wait for that. Okay, and the analysis has been completed now. So this became green, map with BWA on data 1 and data 2. And this is actually the typical sum format. So we'll go through some flags of it, some lines. So these are just the header, we will not go through that, but the real information actually comes from this line onwards. Now this is the name of the read, and this is a code that I must explain. I will explain later in a separate video in detail, and these are actually converted binary codes, and it informs us for different things. So for example, this one might say that we have per dent and the second mate is okay, and so on. It requires definitely a separate explanation. Now the third column is the name of the chromosome. then I'm not sure what this number is here, this index, but this one is what is called the cigar strings and informs us about how mapping has been proceeded. For example, the 36M means that all of the 36 base pairs that we have here have been mapped to the reference genome, one next to each other. So maybe this one is a chromosome. I must find out what these numbers are. This is our sequence from this first read. This is the quality score, and here are some additional flags that again I will explain them in a separate video. So since we have this, actually we have already the mapping. So yeah, here, if I remember well, let's see, this is the position of the mapping, right? Somewhere here in some column, but I don't see the index of the columns. Yeah, here they are, flag, rname, pose, mapped, cigar, and pose, and so on. So somewhere here must be the position and the chromosome of the mapping. Insert size, position, so this is mapped in position 1, and then pose might be the position of the mate. Yeah, so probably what we see here is the following. Let me see, let me check. Yeah, I will come to this later because I don't want to say anything wrong here. So we have done the mapping already, and now we can visualize that in a browser. There are several ones. For example, you can use IGV browser. I have it somewhere here. So this is the visualization of this data in the IGV browser. So if I will zoom in or out a little bit, you will see what I'm talking about. I think that I have specified the this one here. So if you see, the data is like that. This is the visualization of the mapping, and what we see here is the following. Here on the top you have the yeast reference genome. I have zoomed in, so this is the whole yeast reference genome, but I just visualize now this small red area. And here you see all these reads in every location of the genome. So for example, you see that there are regions that have been covered a lot by reads and regions that have less coverage, like here. Now the IGV uses this color code here. Let me remove this. Okay, so if I zoom in a little bit, here it says that where is it? Yeah, so here it says that the mate is mapped as well, yes. And between this read and its mate there are 2 KB, more or less 2 KB base pairs. So this is the insert size. So this insert size is, so if we have here the genome, and we have the mapping of the left of one mate 1, and here we have the mapping of the mate 2, superdent, right? So this one here is 2000 something base pairs. This number here, 2127, which is pretty long, which means that we have actually quite long fragments, right? Because we said that from a fragment we read one end and the other end, which means that we have quite long fragments here. In IGV, a different way to visualize things is by using this paired view as pairs. Here it is. So now we see actually the pairs. If I will zoom out a little bit, you see, for example, that this is one mate, and somewhere far away here is the other one. Let's see if we have some closer. So this is one mate and this is another mate here, and yeah, this is one mate and this is the other one, and it's color coded based on the distance on the size of the insert. So you see that for small ones we have the gray, and for long ones we have the green here. Now the insert size might specify the insertion or deletion, and that's why it's different color coded here. Indeed, if we go to the help page of IGV and then we go here to interpreting color by insert size, we read here that the inferred insert size can be used to detect structural variants such as deletions, insertions, or interchromosome rearrangements. And then here, so in the case of deletion, the inferred insert size is greater than expected insert size. In IGV, such an event might look like the following. So why a deletion is, in the case of deletion, the inferred insert size is greater than expected is because the deletion here has happened on the fragment of our sample. So we have the deletion there, but we don't have the deletion in the reference. And therefore, when we map the read to the reference, the one mate will be far away from the second mate, just because there is deletion on the sample but there is no deletion on the reference, and that's why there is here this greater than. Okay, we can visualize the data in IGV, but we can also use a tool that is here, and it's called jbrowse. So jbrowse, genome browser. And again, we have to use here Cerevisie. And we can use the minimal viewing if we want to use standard code or some special genetic code, for example vertebrate mitochondrial, yeast mitochondrial. We will use the standard code. We have yeast, not the mitochondria. And then track group, here we have our data. So jbrowse can visualize again different things, and we say what we want to visualize, and what we have is mapped files, right? We don't have GFF, which is our annotation. We have BAM pileups because BWA created these BAM files. Okay, automatically detects that we have this data, so I select them and then I just click here execute, and again we have to wait, and meanwhile we can read this cartoon from PhD Comics. Okay, everything seems to be fine, finished. So I click this display here, and so if I zoom in, okay, this is the reference genome, what we see here. I will zoom in a little bit more just for you to see that. So this is the reference genome, and it's, it's a complementary strands here. And what you see here with the strange whatever code it is, it's actually the different open reading frames. So these are amino acids, 6 of them. We have 6 reading frames, 3 for the forward and 3 for the reverse complement. And here on the top of that, or on the bottom of that, I will just put the reads. It's the same image that we saw previously with IGV. I will zoom out a little bit. And again, you see this pile up of reads at every location of the reference genome. So for example, this region has been covered quite well, but this region has been covered a little bit not so well. And then we can click here and modify the way that we see things. So for example, I can go here again and view result as pairs. Let's wait for a while. And again, you see that, zoom out. You see that you have the mates, and sometimes the distance between the two mates is quite small, and sometimes it's really huge, like here. I don't know if this is a specification of the data. Normally, when we use normal libraries, Illumina, the fragment size is about 500-600 base pairs, so we should not see something like that. But perhaps they have generated a very special library here. So I see that we have very small fragments and very large one fragments. Perhaps they have combined Illumina with some other technology. I don't know exactly what they have done here. You see that there are regions that are not covered that are covered quite badly, like here. Perhaps there is a deletion on the data compared to the reference, or it might be because we have just used a very small part of the data, just 1 million reads. Probably there are many more million of reads here. It's crashed. Let's see. Let's load it again. Yeah. So yeah, that's how it is. Okay, and with that we finish this part of the lecture. That just to summarize what we said in this small video, we perform the mapping with BWA, and we visualize the mapping either immediately as a SAM file or in IGV or in jbrowse. Thank you very much.